In this lesson, we will discuss the case of the motion of connected masses. I have two trolleys here. I have connected them by means of a string. If I apply a force on one of them, you notice that the force applied on the first will make it move, and then it will stretch the string. There will be a tension on the string. And what will happen? Well, my string fell off. Well, the tension on the string is going to pull the next mass. Now, therefore, what will be the net force on the trolley in front? The force I apply will be forward, and the tension at that time, the tension on the string is going to pull this trolley back. So the net force on this trolley will be the applied force forward minus the tension on the string. And that net force will produce an acceleration on this object. Now, what will be the net force on the second trolley? It will be the tension on the string, because it is the tension on the string that pulls the second trolley. Now, when you deal problems like this, connected object, what you need to do is isolate each object, figure out the net force on it, and then set the net force equal to ma. So isolate this object, the net force on it will be the applied force forward minus the tension force. That will be equal to mass times acceleration of this trolley. For the second trolley, the force on it is the tension, and that will be equal to its mass times its acceleration. Now tell me, if this system is made to move with an applied force like this, what will be the acceleration of each of these? It will be the same. Well, this is one type of connected masses we will be looking at. Another type of connected masses we will be looking at will be this, where you have a pulley and two masses are suspended by means of a string. Alright, and if the masses are not the same, you can see there will be relative motion. Is that right? Now, this is slightly heavier, so that's going to move down. Again, we apply the same principle. We take each object and find the net force on it. Now tell me, what is the net force on the object that I'm holding now? Well, the weight of this object will be acting vertically down, and the tension on the string will be pulling it up. And in this case, that tension is going to win. You can see the tension is pulling it up. On the other hand, the one on the right, the weight will be acting down and the tension will be acting up. But the weight is greater, therefore the net force on this will be the weight minus the tension. Alright, I'm talking about the magnitude only, not the direction. So in each case, obtain the net force and set the net force equal to ma, and that will help us to solve problems. Okay, let's look at each of these. So, in order to solve problems using connected masses, we first isolate each object, identify the forces acting on each of the objects, and then apply the laws of motion in each case. Well, of course, the law of motion is the net force equal to ma, and we produce equations and solve those equations for the unknown. Let's take a simple example. 3 blocks are pulled along a frictionless horizontal surface, applying a force of 18 Newton as shown here. Now there are 3 trolleys here. They are connected by means of, you can see that yellow that is there is the string. And applied force 18 Newton pulls the system forward. What do we need to find? What is the acceleration of the system? Now, when you consider the system, the whole system has a total mass of m1 plus m2 plus m3, and that total mass is being pulled by 18 Newton. So how will you find the acceleration of the system? Alright, I'm going to leave it for you. And what are the tension forces on each of the pieces of strings? What is the tension on this string and what is the tension on this string? Okay, let's first deal with the first case. What is the acceleration of the system? Let's say the tension on the string connecting the mass m1 to m2 is T1. And you notice that the direction of T1, when you look at the motion of M2, that T1 is pulling it back. Whereas when you look at the motion of M1, T1 is pulling it forward. And the string that is connecting M2 and M3, let the tension be T2. And look at the directions of that T2. When you consider the motion of M3, that T2 is pulling it back. Why? Because that T2 is pulling these 2 masses. That means it is pulling this M3 back with that T2. But when you look at the motion of M2, that T2 is pulling it forward. So you must be able to understand the directions of these tensions. Now notice here that T1 pulls M1 to the right and M2 to the left. I hope that is clear. The tension on the string connecting the masses M2 to M3 is T2. T2 pulls M2 to the right and M3 to the left. The total force F net equal to 18 Newton pulls the whole system of mass M equal to 1 plus 2 plus 3, that is 6 kilogram, and therefore you can now use F net equal to ma and find the acceleration of the system. A equal to F net over m, that will be 18 Newton divided by 6 kilogram, and that is 3 meter per second squared. The acceleration of the system is 3 meter per second squared. What does that mean? It means the acceleration of each of these masses is 3 meter per second squared. The acceleration of m1 is 3 meter per second squared. The acceleration of m2 is 3 meter per second squared. The acceleration of m3 also is 3 meter per second squared. Okay. Now we take each mass separately. Separate each mass and identify the net force on it. Let's take the 1 kilogram mass, the one at the very back. The only force acting on that is the tension T1 pulling it forward. Is that right? That's right. So F net on this mass is T1. The tension T1 produces an acceleration of 3 meter per second squared on this mass of 1 kilogram, and therefore we know that F net equal to ma, T1 equal to, T1 is the net force, and that is equal to ma, mass is 1 kilogram, acceleration is 3 meters per second squared. So T1 equal to 3 Newton. Alright, let's now talk about M2. What are the forces acting on M2? Well, T2 is pulling it to the right and T1 is pulling it to the left. Is that right? This tension T1 will be pulling M2 to the left and the tension T2 will be pulling it to the right. So to find T2, we isolate M2. The forces on M2 are T2 to the right, there you are, and T1 to the left. Therefore, what is the net force on that mass? The net force is T2 minus T1, and that net force must be equal to M2 times A. M2 is 2 kilogram, acceleration is 3 meters per second squared. So T2 minus T1 is 2 kilogram times 3 meters per second squared. That is 6 Newton. We know T1 already. Is that right? We calculated T1. You remember how much was it? It was 3 Newton, wasn't it? So T2 equal to T1 plus 6 Newton, and therefore T2 equal to 9 Newton. Alright, I think we now found the tensions on each string. You can see how simple the problem becomes once you isolate each object, identify the forces acting on each, and then apply the law of motion, and we can calculate the unknown forces. Alright, next we will look at connected masses. Now this, I just showed it to you how the system looks like. Well, let's have a look one more time how disconnected mass looks like. Let's talk about the motion of this system. Now, I'm talking about my side. Now, there is a mass on the left, there is a mass on the right. The mass on the left I'm going to call M1, and the mass on the right I'm going to call M2. Now tell me, the tension on the string, will the tension on the string on each side be the same? Well, it will be, provided there is no friction on this pulley. So the tension on the string on the right and on the left are the same. Alright, now tell me, the mass on the left is M1. What is the net force on this mass? I told you that the net force is its weight. What is the weight of M1? M1G, is that right? And there's a tension force acting up. And since it is moving up, we know the tension force is greater than the weight. So we can say the tension minus the weight equal to, that is the net force on it, equal to MA, where M is this mass and A is the acceleration. Similarly, we come to this mass, we can say M2G is the weight acting down and the tension is the force acting up. And in this case, the weight is winning, and therefore we say, remember, we are only looking at the magnitude, not the direction. The weight acting down is a greater force, so the weight minus the tension equal to M2A, mass times acceleration. And is the acceleration of these two masses the same? Yes. There you are. The magnitude of the acceleration is the same in both cases. We can actually obtain equations using these two masses and calculate the tension on the string and the acceleration of the system. Alright, let's in the example here I have used specific masses.